I'm Eric. I'm a recovering typeholic. And I kept when I look at this conference, I'm super impressed by all the work that's done. But I can't wonder, how is it possible that after so many decades of these conferences, we still don't know how to write code? Why do we still need conferences like this? Shouldn't this be a solved problem? I don't know. And yesterday, again, as a recovering typeholic, the keynote was very tempting. I was ready to jump off the wagon again and start doing all that type stuff, beautiful, dependent types, it had Haskell in it. It was I was so tempted. But then I remembered, yes, long time ago I did Haskell, then I went to VB, to C#, to Visual Basic, to Dart, to Hack. I'm so much in the gutters, that's unreachable for me. And in fact, it's unreachable for a lot of people. If you look at a lot of these things where we're doing program verification, it's really cool, but it's hard for the regular people. If you can look outside the window here, you see all the skyscrapers, and there's probably people there hacking JavaScript and CSS and building business applications, and those are people that have a hard time even doing their job, and so that's the audience that I'm trying to address. And where's my... So one of the things, for example, say that I want to do this. This is, I think, something that people want to do. So I want to get, recognize pictures of cats and dogs. And it kind of looks simple, right? Yeah, everybody sees that's a cat, that's a dog, so it should be easy. Should be easy to do that. Now, if we would like to try to write a specification, how would that look like? Well, say that I want to filter pictures that have cats or dogs. I can give it this type, so it's okay, take a picture P, and just only keep the ones that are pictures of cats or pictures of dogs. Now, of course, I still don't know how to ever specify how, what is a dog or what is a cat, except for, how do you do that? Right? So how do you write a formal specification that tells you if a picture is a cat or a dog? What's going on? Whoa. So what my thesis is that extensional specifications are hard to create. You have to write a formula that describes what you're doing. So why not do a slightly different form of specification, namely write an intentional one? Now you think Eric, I thought you were targeting normal people. What does intentional mean? Well, that just means give a bunch of examples. All right? So that's what we want to do. It's can we program by just, instead of writing complicated formulas that specify the values that we're interested in, let's just give a whole bunch of examples and see if we can then use whatever methods to from these examples, generate programs that we are interested in. And I think that's a very powerful way to develop code. So again, looking at this thing here, you can take a bunch of pictures and you can label them, and now you get examples, and then can we use that to generate a program that will then recognize cats or dogs in these pictures. But now let's take a step back. Let's take a little step back to see why is programming so hard. So why did it take 50 years of conferences like PLDI, and why are we still struggling to specify our programs? And in yesterday's keynote, it's when one of the questions was asked, can we do this for other languages, unlike Haskell, can we do it for concurrency? And then the speaker kind of scratched his head, yeah, well, and I think the reason is that we are pretending that we are dealing with mathematical abstractions, whereas in reality, we're programming physical machines. And these physical machines are based on one principle and one principle only, namely moving bits from one location to the other. So these machines are inherently very stateful and very imperative. And you can get you can look at whatever x86 or whatever RISC machine. If you get look at the essence of these machines, that's what they're doing. They're moving bits from one location to the other. And on top of that, we're trying to build layers and layers and layers of abstraction, but we can never get rid of the fact that that's really what we're doing. And if you're writing code, ultimately you want to make it efficient. Anybody here that tries to write efficient code, you have to know about that layer of physical machines. You have to know about the memory hierarchy. You have to know about the caches. You have to know about how do you can most efficiently move stuff from here to there. You have to know about is this in one side one core or between cores? All these things you have to deal with, and your mathematical abstractions fall to the ground. And I was talking with some PhD students over lunch, and they say, oh yeah, we're doing static analysis to check the distance between memory locations to make that more efficient with the cache, blah blah blah. That's all great, but again, what you see is that we're kind of fighting this abstraction that's basically broken. The other, I think, abstraction that's broken is the model of our objects are mutable edge-labeled graphs. So that's the things that we're kind of dealing with. So on top of this machine, we're building this abstraction of mutable edge-labeled graphs. And then our functions, our programs that we write, are not really functions. They are side-effecting procedures. So we can pretend that they're functions, but they're really not. And even, I think, in yesterday's keynote, even in Haskell, you cannot say that this thing is just a function, because in Haskell, every value has bottom. So you always have to deal with non-termination, and you have to get, always make sure that you deal with that case too. So even Haskell functions don't correspond to have simple, total mathematical functions. And even there, the fact that we're running computations shows. And because of this, we have to invent our own mathematics. We have to invent our own formalisms. And that's why conferences like this are there, because we can invent new logics, separation logic, this and that, because the abstractions that we're working with are artificial. They're machines and then we're trying to get reason about them. And Tony Hoare already noticed this in 1972 when he was talking about you have an abstract function f that you want to implement in terms of some concrete function g, and now you have to get make this diagram commute by giving concretization and abstraction functions. But this thing, again, this is a great paper and this is a great idea, but what this doesn't show is that always that there's an abstraction leak. And so again, you cannot really formalize it as cleanly as this. So this is, I think, the way I look at the world. We have, von Neumann's P at the bottom, and then we're trying to build layers and layers of abstraction, but we will always feel that P. There's no way to escape that. And for many years, I thought, okay, Eric, we can get we can get there. Until I realized all this declarative programming, all that stuff, it's not going to work, because the P we will always feel that darn P. And so, at some point, I said, okay, maybe we should look at a very radical different way of programming. And that's the way of programming that I kind of like referred to in the beginning. Can we, instead of doing this kind of like complicated mathematics where we're trying to kind of like put lipstick on this imperative pig, can we kind of like, build programming on simple mathematics, old-fashioned mathematics, mathematics that's been kind of like there for centuries, that like, people have done forever, mathematics that you learn in high school. Wouldn't that be much nicer if we could build our whole kind of like field on something much more simple? So that's kind of like, I think, is possible, because otherwise we will keep kind of like trying to push the stone up the hill, and it will come right rolling back to crush us. And of course, my brain is the size of a peanut, so I kind of just like, I can just not handle that. So I really need like mathematics, simple mathematics, and really simple. I really mean basic mathematics, right? Mathematics that every high school kid can handle. Now let's look at another example where simple mathematics has been super successful. And that's relational databases. If you look at relational databases, that is based on ancient math. It's based on relational algebra, which is literally just simple set theory. Everybody can understand that. Oh, I can filter from a set. I can map a function over a set. I can like do a join. All these are very, very simple operations that work on very simple mathematical structures. And if you look at relational database, the implementation is pretty faithful to that abstraction. It's not really, because most databases really don't work on sets. They work on multi-sets. But still, I think if you take a course on databases and they kind of explain relational algebra and then they say that's the basis of your database, your professor is not completely lying. I think they're lying less than when you're talking about like, imperative programming or functional programming. And because of this simple mathematics, relational databases are extremely effective, right? You can really write like a high-level query, and you can use the algebraic properties of the underlying relational algebra to optimize your code and make it faster. And I don't know, I haven't looked up like what the current like revenue is for for relational databases. Maybe that has gone down because like everybody's using open source databases these days, but I don't think that the economy could like function without relational database. Probably everybody's salary here in this room requires a relational database to be computed. So the whole economy would crash if we would remove relational databases. And I think this is because of the fact that it's based on super simple mathematics that actually makes it easy to do declarative programming and makes it easy to optimize SQL queries. So that's, I think, what I want to pursue is is there simple maths that we can use to make programming more efficient or easier to do? And another thing, I think, what I notice is that there's a an explosion in the world of programming today of frameworks. If you're a JavaScript programmer, there's every day there's another UI framework. And even in the programming languages, there's an explosion of languages, which is great for us because we can write papers about them. But these programming languages are really, if you follow Strachey's advice and you would look at the denotational semantics of these languages, they are all more similar than different. And maybe the difference is in the type systems, which is interesting, but semantically, they all remain essentially imperative languages. And a lot of these modern languages like Rust and so on are really trying to get, they're trying to fight von Neumann's P, but we cannot get rid of that. So, what's next? Well, what's next is what people call software 2.0. And software 2.0, there's this blog post, and what Software 2.0 does is that it takes this other approach. It takes the approach where you specify your program in an intentional way. You give it examples, and from these examples, you get you come up with some magic way to create a function that will compute, that will generalize from these examples, and you can feed it new values, and it will then give you new outputs, and then you hopefully for all the values that are in your examples, it will still give you the same values. All right? So it's trying to generalize a function from these examples. And I think that's a very, very powerful way. And again, think back at the example of the cats and the dogs. I should set up a price. It's I will give I don't know. I'm not going to promise here $1 million for people that can do this, using formal methods or something. But I think, if I would give somebody here $1 million to say, okay, now formally specify how to recognize a cat or a dog in a picture, you wouldn't be able to do that. So there's a whole bunch of algorithms. So even if you even if you still love formal methods and you still think the old ways are great, think of this. There's a whole bunch of new possibilities that we can do when we embrace this this intentional specifications, where we're looking at examples and then somehow magically come up with an algorithm or a function that can compute this. And the great thing, as I will show later, is that these neural nets are actual functions. These are pure functions. So in some sense, functional programming will rule the world, but it's not called Haskell or OCaml or whatever. It's called deep learning. Deep learning, these neural nets are actually side effect-free functions. And that's also amazing. The other thing is they always terminate, they run in constant time or whatever. But so I think, again, if you love functional programming, you've been looking in the wrong room. You should look in the other room where functions, simple functions, are ruling. So here's a picture of the old world and the new world. So the old world, people would humans would take coffee and specifications and turn them into code. And the new world is we take data and we have some magic process and we turn that into a model. Now, the machine learning folks like to call these things models, but really there's no real difference in my view between model and code. There's a little bit of a difference that I will talk about later, but really it's just like a function that you can generate from this. Now, this when I discovered this thing, this is the moment that I really thought there is something here. Let's look at this database thing again that I talked about. What is a database? Well, it's something that I send code. The database people call that a query, but it's really code. And the database sends me back data. Right? That's what the database does. It's a magic machine. You send it a query, and it gives you back code. You don't have to know how this database thing works. You just give it code, it gives you back data. Now, what is a machine learning algorithm? It's the dual of a database. It's a magic device where you give it data and it hands you back code. So really, machine learning is the dual of databases. And that's an interesting observation. What's even more interesting is that if you look at the parts of a query that you're interested in, say that you got you look at this typical SQL query, it has a predicate because you have a where clause you're trying to filter, and now maybe you don't know how to write that where clause. Well, you can use machine learning, say spam filtering or whatever, Bayesian spam filtering, that gives you a Boolean, yes or no, to find that predicate. So you can fill in that hole in your query that you don't know how to write by inventing that function using machine learning. Or if you have a group by, what do you have to do? Well, I need to partition my data into groups. I don't really know how to find these groups. Well, you can do there's like many machine learning algorithms to do kind of like grouping, right? So it's also interesting that if you look at all the parts of the query, each of these functions have a natural correspondence in the machine learning side. So not only is query dual to machine learning, it's also kind of like, there's a deep connection between these kind of like, the parts of the query and the way and the kind of like different machine learning algorithms so that you can plug them right into that. Now, so the question is, we know how to do the things here on the left-hand side. We know how to turn code into data. Can we also turn data into code? And as I promised you, we can do this with really, really simple math. Everybody that's sitting here, I think most people here have been through high school math. All you need is high school math. And that's the kind of beauty of this. So let's do the kind of like simplest thing that we teach in high school to every kid in high school. It's like how to do linear regression. So linear regression, you get a bunch of points, and you have to find a function, a linear function through those points. So given like a bunch of x and y, you have to find a and b. And then, because the measurements are noisy, there's some errors along the way. Some people kind of say machine learning or this kind of deep learning is just curve fitting. I think that's exactly what it is. That's fine for me. These curves can become very complicated, so I don't care whether you call it that or maybe it's really basically what you're doing. That's fine. I don't think that neural nets have anything to do with intelligence. They are just devices where you throw some data at it and it gives you a function. I don't think there's any intelligence or anything that has to, like our brains don't do matrix multiplication. All right, so this is what we're having to do. Let's write this a little bit as a higher order function. So we have a function f of a and b, and it returns a function that takes an x and then computes, a times x plus b. And what we have to do is, given training data, a set of xi's and yi's, we have to find a and b's such that it minimizes the error, the sum of the squared error. So this is kind of like, another thing, or this is another thing. So when I say that, you just throw the data at this thing, there's also, and that's why the title says Alchemy, there's a lot of black art here. So like, how do you find this error function, this specific error function here? Well, you just pick this error function. For other things, you pick other error functions. And that's also why I think this field can use the help of programming language people. There's a lot of things that are not very systematic in the machine learning area, where we as programming language people, we are used to kind of doing things very systematically and in a very formal way. And the machine learning field really needs us. It needs us to kind of make these things more precise, to kind of reason about these things and don't make it like magic. But for now, let's just assume that this is what we're doing. So what you do is then there's this thing called gradient descent, and that relies on the derivatives of this error function. So you take the derivatives of this error functions on a and b. The way I do it here is I just go to Wolfram Alpha website, I type in that function, and it will give me the symbolic derivative. In a few minutes, I will tell you how to do this in a different way, a better way. And the gradient is the pair of these derivatives. Again, this is all high school math. We know how to take derivatives of these simple functions. And now we see that we're still doing some imperative programming here. Because what we're going to do now is we're going to kind of go over our training set, and we're updating the weights based on this on these gradients and some learning rate. And we're just kind of going to do that until we run out of training examples, or sometimes people do this until the error is below a certain value. And then we just return A and B. So notice that machine learning or deep learning still does update. So it still kind of like is imperative. But all the imperative stuff is done in the training phase. Once I have A and B, let's look here. Once you give me A and B, oops, now I have a pure function, right? I really have an actual, real function with no side effects. So all side effects are pushed into the training side, and then after that, this thing is kind of like completely pure. So I think it's a really nice way where we're still using mutable state, but the mutable state is kind of like completely isolated from the thing at runtime. Okay, let's talk a little bit about these derivatives, because I think there's some really interesting things going on here. So we all probably remember from high school that you use derivatives to find the minimum of a function. So here I have a quadratic function. I take 3x squared plus 4. And then, where the derivative is 0, that's where the function has its minimum. That's what we did in physics class, right? You throw a ball and you have to find where's the highest point of the ball. That's where the derivative is 0, things like that. Now, the traditional way to define the derivative is this this division. So you take f of x plus epsilon minus fx divided by epsilon x plus epsilon minus x, and then you make epsilon go close to 0. If I compute the derivative here, then you find that the derivative function looks 6x. Of course, you could have found this immediately if you would do symbolic derivation of it. You would say, okay, that's 6x, and then all the rest falls away. All right? So, but the question is there a smarter way? Is there a better way, a nicer way to compute these derivatives automatically? And it turns out that that's the case. But for that, we need some more math. But this is also really, really ancient math. And that's what I liked, right? This is we don't have to invent anything new. Everything was already done centuries ago. And this is I think this for me is a thing of supreme beauty. Everybody here remembers complex numbers. And complex numbers, if you think about them in a syntactic way, if you don't try to interpret them as something that's has to deal with angles or something, just look at them as a data structure, as a pure purely completely syntactic. Don't try to interpret what these things are. Okay? So what is a complex number? It's a pair of numbers, A and B, or A plus B times I, where I squared equals 1. Okay? And you just you just make a choice. I squared equals minus 1. That's just a random choice. And now you can compute with these things as if they were numbers. And if you multiply them, you just use the rules of multiplication. And then if at some point in this term you get an I squared, you just replace that by minus 1. That's just how you defined it, right? And again, it turns out that this thing is super useful. It's used in electronics, physics, whatever, graphics. But again, think of these things as purely syntactic, where I'm just imposing some arbitrary rule like I squared equals minus 1. Now let's do exactly the same thing, but define, and just to avoid confusion, instead of I will use epsilon. Let's just define epsilon squared to be 0. Why not? Right? If we can define I squared to be minus 1, why can't we define it to be 0, right? There's no reason that it can be. Or we can also define it to be 1, if we want to. That also turns out to be useful. That's called hyperbolic numbers. You can Google that. But if we take epsilon squared to be 0, it turns out that we get something super interesting. So let's just do an example. So let's take our function f that we defined over here. This function here, 3x squared plus 4. And let's just apply that to this number, to a plus b epsilon. All right? And again, let's just compute this. So that's like, x is now a plus b epsilon. So this becomes 3a plus b epsilon squared plus 4. And we just go and do simplify that, just simple arithmetic. And then, we end up with this kind of previous to last line. You see there's like, on the far right, there's 3 epsilon squared. That becomes 0. And then let's now look at this thing. So what we see here is that 3a squared plus 4, that is really just f applied to a. And if we look at like 6a, that was exactly the derivative of f applied to a. Wow. That's magic. And is this just a coincidence? No. It turns out that for every function, if I can lift that function to dual numbers, what it will do is it will compute a pair of the function applied to the first value of that pair to a, and the derivative, the first derivative of that function applied to a multiplied by b epsilon. Isn't that amazing? Just by taking this epsilon squared equals 0, we suddenly get a way to get derivatives for free. Just completely for free. Now you will say, Eric, yes, that sounds great. How can we prove that? Well, for that, you can use Taylor expansions, which is even a weirder thing. I don't know, this person must have taken mushrooms or something, because if you look at Taylor expansions, this is 1715, right? And somebody comes up that, I can take a function f and write it as this infinite sum, and that's that gives you if you do it far enough, into infinity, it will behave the same as that function f. And that's amazing. I don't know. I look at that formula. Have you ever, if you have seen Taylor expansion, have you ever wondered how can somebody come up with that? I think this is amazing. this is mind-blowing that somebody can come up with that. But let's just do the Taylor expansion on f and a plus b epsilon. And then kind of what we see, because epsilon squared equals 0, is that all the terms, that when n is larger than 2, all kind of just drop out. And we really get, f plus f squared, or f prime, the derivative of f applied to a times b epsilon. All right? So there's really kind of this relies on the Taylor expansion. So what do we have here? We have a functor. We have a functor here, and the functor lifts f, which is defined over real numbers, to these dual numbers. Okay? And this is quite nice. So we have found a functor that will automatically compute derivatives for us. And if it's a functor, well, it should distribute over function composition, and it should maintain identity. And if you remember the chain rule, and if you don't, I'll show it on the next slide. You kind of remember the chain rule. I can never remember the chain rule. The chain rule says how you take the derivative of a composition of functions. It's always something kind of weird, and I always have to Google for it. I cannot remember it. But here, look at this, how beautiful, right? This thing, just because it's a functor, it nicely distributes over function composition. And what we will see is when we try to prove that this thing is a functor, we will have to use the chain rule. And you see here, the chain rule there is if you take the derivative of f composed g, it's something that has a multiplication there and a composition of the derivative with this other function. It's a mess. But again, if you just do the simple equational reasoning, you use the chain rule right in there, and you see that these things are, it's a nice functor. So what does this mean? Well, this means that if I have a function that is composed out of smaller functions, and each of these smaller functions is differentiable, I can now, because of this lifting is a functor, I can find the derivative of that big function by simply applying this functor to it and just computing it as we go. And this is what people call automatic differentiation. Okay? So automatic differentiation is really easy. You just lift values into these pairs of dual numbers where epsilon squared equals 0. Let me just grab my phone, see how we're doing for time. Good. All right, so of course now we need to look at all the other operators. So like we need to define addition and multiplication and everything for dual numbers. But again, we can easily do that by just simple, basic, this is not even high school mathematics, right? I mean, if you have children under the age of 4, they could do these derivations. Right? That is amazing, all right? And again, like, you know, look at division here. You just say like a plus b epsilon, this dual number, divided by c plus d epsilon, the other dual number. There's one little trick that you have to do here. You have to multiply this thing by 1, and then you just take c minus d epsilon divided by c minus d epsilon as 1. But you compute the whole thing, and you get this term here, for the division of two dual numbers. And if you squint a little bit, you will find that really that's kind of very similar to the quotient rule, which tells you how to take the derivative of two functions, of the division of two functions. And you see the square down there, and you see the the fact that there's b times c and minus a times d, that corresponds to the derivatives in the quotient rule. All right? So who knew it was so easy, right? Coming up with the quotient rule, that must be a nightmare. But coming up with the division of dual numbers is super simple. Same thing here. If you look at the product rule was also Leibniz came up with that in the 17th century. Again, you look at that, it's wow, this guy must have been smart. I couldn't come up with that. But again, if you just compute the product of two of these dual numbers, you will find easily what that should be. And then the other thing is for other operators like sinus, for sine, you just you just follow the rule of lifting this thing, right? So it's just the function applied to a, and the derivative applied to a times b epsilon. So for sine, that becomes sine a plus cosine of a times b epsilon. And so for all the other operators, you just define it like this. And because this thing is a nice functor, you can just use operator overloading. So if your language allows operator overloading, you can just just define all these operators on this new type, and off you go. You have automatic differentiation. Okay? Now, what happens if you look at these neural nets? They are usually not simple functions that I showed you here that take a real number into a real number. They always take a vector of real numbers into a single real number, because you have a function that you compose with the error function, and that error function returns a single real number. And if you use these dual numbers that I just showed you to compute the derivatives with respect to the weights for all of these, you have to run this. You have to compute if you have n weights, you have to compute n times this function. You can vectorize it, but you still have to compute it n times. So forward differentiation is kind of slow. If you go backwards, and that's why people call it back propagation, then you can do this in one pass. Now the question is how do you do back propagation with dual numbers? And what is interesting, and there's a quote by somebody that good ideas spring up like daisies in the spring or something. I don't know who to attribute this to. But a lot of people have recently discovered that back propagation is just CPS conversion of forward propagation. So let me show you. And this is a complete abuse of types here. So if you look at these dual numbers as a pair of two numbers, a and b, let's replace that second number by a continuation by a function that takes a number and returns unit. Okay, this is just plain, like, vanilla CPS conversion. Okay, so instead of taking a pair of two numbers, I now have a pair of a number and a continuation. And the continuation takes a number and returns unit. So again, we got, like, if you're a Haskell programmer, you know that a function that returns unit cannot do anything except doing side effects. So in the actual implementation of backpropagation, you will have to introduce mutable state to get, like, accumulate the gradients, but it's still just vanilla CPS conversion. And so let's look here at an example. If I can, like, define sine, so instead of, like, saying, instead of the previous definition, I just still compute sine of A, but now I kind of do the cosine of the continuation times epsilon, where I define multiplication of this continuation with the value to be this callback that takes a B, calls the callback by multiplying B by the cosine of A. All right? So this is just like, if you look at this is really just vanilla CPS conversion on these dual numbers. And there's a whole bunch of papers, I have a couple of, like, references later that show you how to do this. But this has been kept, like, reinvented several times. Okay, and here's, like, multiplication. So you can do this all using operator overloading. So here's how we can, like, can implement this magic machine that turns data into code. We can, like, we define a function, a composition of functions. If all these functions are differentiable, we know if we implement them using dual numbers, and if we use these dual numbers that use CPS, that we can find the derivatives automatically. And then we can, like, we pump in, like, one training value, and we get back the error. We use that to kind of update the weights, and just rinse and repeat. Okay? So this model that people talk about is really just a composition of differentiable functions. And if you look at most deep learning frameworks today, they are not composition of functions. They are compositions of layers. There people kind of compose data structures instead of functions. And I think it's a very liberating idea to look at these neural nets as just really, it's functional programming. Right? It's functional programming with special functions that are differentiable. And what is differentiation? It's simple. It's just kind of like, CPS conversion on these weird things, these weird sisters of complex numbers, where instead of I squared equals -1, you say I squared equals 0. Okay? And what is a neural net? That's just a special case of this, where the functions, this composition of functions has a special form. And why do people like this special form? Not because it has anything to do with neurons, but because it has a lot of additions and multiplications, and we know how to do that fast using GPUs or whatever. Right? So I think that's the whole reason why people like neural nets or use these functions to define neural nets, because you can efficiently compute that. All right. So differentiable programming is programming with composition of differentiable functions to define models. And there's a lot of things here. There was in the workshop before, there was a talk here about a new IR for machine learning frameworks. Guess what they did? They used CPS conversions to do the kind of auto differentiation. Simon Peyton-Jones has a recent paper where, even Simon Peyton-Jones is kind of leaving the field. He's not doing Haskell anymore. He's now doing differentiable programming. So that should be a sign. That should be a sign. But what he's trying to do is he's trying to say, I can do forward propagation if I do get enough program transformations. And if all the differentiable functions that I write are faults. But this is very interesting. But to me, the most interesting thing is that even Simon is jumping on this hype, which means that it's probably safe for everybody to do it as well. And so there's a lot of papers about this stuff here. All right. So let me finish my talk here. We're running out of time by saying that, I lied a little bit to you. Because these models only approximate a function, right? So they're not really functions, because they're kind of doing a lot of guessing. So there was this error. So you don't always get the exact answers. Now, of course, as I said in the beginning, even for the functions that we write, that's always the case. Because whenever we say in OCaml or in Java or whatever, we write a function from A to B, really, we write a function of A to some monad, something that describes the effect to B. So every function that we write in a traditional language is also an approximation. It's not a real function in the mathematical sense, unless we can make the effects explicit. We can do the same thing here for these models, and the way we make the effect of this thing being an approximation explicit is by having it return a probability distribution. All right? So there's nothing new under the sun here. So the old school programs use monads to say there's an effect. These models use monads to kind of say that there's an effect. But this is the probability monad. And again, I showed functors, so I have to show monads as well. No talk without monads, even if I'm bashing functional programming. And so this is the probability monad. I won't talk much about it, except that if you look at a lot of the things that people do with these, and I show a little bit of this, what people do with the probability monad is based on base rule. And base rule is another piece of crazy mathematics from centuries ago. It's 1763. And what that says is that if I take the bind of the star that's really bind, and the P of B given A, that's a monadic function from A to probability of B. Maybe I should yeah. So here's the type. So P of A, that's just a value of type probability distribution of A. And then the star, that's just monadic bind. And if you look at base rule, really what it says is that it gives you a way to invert a monadic function. Because on the left there's P of B given A, which is a function from A to probability distribution of B. And on the right, there's P of A given B, which is a function from B to a probability distribution of A. So this Mr. Bayes in 1763, without monads were not even invented, and he already has this super powerful theorem about monads. He must have been an alien. I mean, this guy must have been dropped from another planet that's evolved much further, and left this as a message for us, and now we can use this to do this probabilistic programming. All right. Since I'm running out of time, let's say what are we going to? Why do we need this probabilistic programming? Why do we need these probability distributions? So let me give you a very simple example, and I can talk to you offline about real examples that we do at Facebook, but here I have to give you a artificial example. And since we showed in the beginning that we can build a neural net that recognizes animals, I want to become rich. So I'm going to write an app that is going to do the following. It's going to use the neural net that can recognize animals, and I'm going to build an app that will tell me whether this animal is petable, is safe to pet. So you just take your phone, you can point it at the animal, and then this thing will say it's safe to pet. I mean, this will be on the App Store, this will explode, right? Everybody with children will want to buy this app. All right. So how do we do that? Well, this is our neural network. It takes a picture, and it returns a probability distribution of animals. And so it should kind of like able to recognize all these animals. Now I need another like machine learned algorithm that uses deep text or something it analyzes text. So it kind of like, you give it a description of the animal and it will predict whether you can pet it. And again, people just like think of this as a spam filter, right? It tells you this animal is safe or not safe. We know how to do this. Like all our email uses spam filters. This is just another form of spam filter. And then I need to have like another function that I need to find that text. So given the description of an animal, I have to go to Wikipedia or some site to get the text that I can then feed into that other machine learning algorithm. But this thing here, because it does a network call, it will return a future. So it has another effect. Because if you go across the internet, things are slow. But now we have a problem. Because I cannot just compose these functions. Because the types don't match, right? First one returns a probability distribution of an animal, but the next function expects an animal. And the call to Wikipedia returns a future of text, and the deep text thing expects a text. So now the tie-dye lamb is kind of like all confused. I don't know how to compose these things, right? But again, because all these things are monads, we can just kind of like, again, like use this is for the first thing I use the bind for probability distributions. I can hook them together. For the second thing, I can use the bind for the future monad, and then I'm done. So that's really what probabilistic programming does. It allows you to get like, to compose these things, and underneath there, it has the probability monad, and in this case, it also combines that with futures, and so you can write code in an imperative style that composes these things. So now, of course, you can say, now I'm back to writing this should be extensional spec. But I'm back to writing code or specifying complex things using probability distributions. But that's it. All right, so that's the second thing here. What I want to do is I want to compose models. So I want to define models using differentiable programming. But then in order to build them into real applications, I need another way to do that. And we need probabilistic programming. So these two go hand in hand. So in order to make these machine learned models useful, we need to have probabilistic programming to glue them together. And again, this I think it's tomorrow. This one was at the Maple paper thing, but tomorrow there's a whole session about probabilistic programming. What you see here, by the way, like a lot of people that are doing probabilistic programming right now, they're mostly doing it to define statistical models, but not to compose machine learned models together. And I think this is a good start. What we discovered at Facebook as well when we started to do probabilistic programming is that there's a lot of demand for building statistical models, but I think the real gain for probabilistic programming is when you use it to compose machine learned models. And people are starting to do that. If you look at Pyro or Edward, that's got deep probabilistic programming. People are using it to combine probabilistic models with neural nets. And I think that's where the real power will be. But again, there's a lot of work on this, and I think that's all super exciting work. You should all go to these sessions. A lot of stuff. All right, so the future of programming is neural nets plus probabilities. Given the time, I want to leave some time for questions. So I think there's a real singularity going on, because the other thing that I didn't have time to talk about is you can use machine learning to improve the programming experience. And again, there's a couple of students here also in the audience that are already doing that, right? So So, and this is what my team at Facebook is also doing. We have some posters back there about like, how to use machine learning to get better code search. And we use machine learning to get do automatic test selection. So we rank tests from high probability to fail to low probability to fail. And we start running them, the ones that have a high probability to fail. Program synthesis, all these things, you can use machine learning to make programming better. So at some point, the machine, the beast will program itself. But I hope that the AI winter will not set in, or this thing will bite itself and poison itself before we reach that. Because I think it's a really exciting time where we can now do things by having these programs that we can train using example data, and then we can use that same mechanism to make our programming experience and optimizing those programs better using the same techniques. So that's super exciting. And we need your help, right? If you look at the machine learning field, we are not yet evolved into the advanced human beings that the programming language community is. And we really need your help. We need to have all the systematic approach, the formalisms, the programming languages, the experience. That's what we need. And you see that. Everybody's hiring. The XAML folks are hiring in this area. The AWS folks are hiring. Facebook is hiring. There's an enormous need for programming language knowledge in this area. So this is a good time. If you're a PhD student or even a professor and you're thinking about changing your career track, this is the right time. No, I'm not joking, right? This field needs, I think the machine learning people now realize that really what they have is a programming language problem. And we should jump on this. We should really take this opportunity and also help them to make the world better. So thank you very much. So that's a good question. So I think there's if you look at the underlying mechanism, it's all based on the fact that you're doing this gradient descent, which is your functions have to be differentiable. Now what is interesting, and I have not, and maybe I don't know the literature well enough, but what people are doing is quantization or discretization. So they when they do the actual inference, instead of using real numbers or floating point numbers, they use 8-bit integers or 2-bit integers, or they go to much more discrete numbers. And the results are still, because you're computing a probability distribution or an approximation, the results are still good. And so I think this is another thing where it would be good if programming language people would come in and explain these things. How does it, how can I take this thing that really relies on continuous math, but it works when I feed it discrete values. And I would love to see a really nice theory of that.
Thanks for the talk. At the beginning, in your provocative opening, questioned the need for conferences like PLDI, or said, why haven't we solved this yet? I was thinking about that during your talk, and I think about building things like a web browser to be used by many people in the world, or building music composition software, or making video conferencing systems. And I would say that while we can do that, and I think the P is actually serving us quite well, things are working, things are on the screen, things are running in our devices, it's still very hard to build these things efficiently, reliably, etc. And there's a ton of things you might want to do that can range from managing the massive code base to working out how to deal with the concurrency correctly in your web browser. So I guess I was pretty convinced by your talk and other work that I've seen in the past about the idea that there are important pieces of functionality for which there's tons of data, Humans are not good at writing that functionality, and machines are going to be able to do it much better and come up with surprising and exciting results. I don't have any feeling, though, for the idea that you could somehow learn how to build Chrome or learn how to build Skype or learn how to build music composition software. There wouldn't be any data. What would an example of an interaction with you could have humans interact with a browser, but that sort of assumes you already have the browser. So I guess I'm kind of thinking, it seems that there's a bit of a, it almost seems like you would partition systems into the very discrete stuff that needs to be planned, needs to be written, does need to be precise. Like, I don't really want something to have worked out really well what it means to transfer money and get it right most of the time. And that's also easy for humans, right? We know exactly what that means. So I feel like you somewhat skirted around the issue that there are some things humans are just good at, and yet it's still hard and still need PL.
I think you're absolutely right, because if you look at this example here, I explicitly also used so this thing here, in order to write a real application, like you're saying, this thing is composed out of things that are machine learned, but this this web service call there to Wikipedia, that's a traditional program. So I think the real trick is yes, the future will be you cannot learn everything, but we will have to find a way to take pieces of software that are learned and other pieces of software that are proven correct, that have to be that do money transactions, and then compose these into bigger systems.
So I guess my question is, do you think in, say, 10 years we'll have a situation where we're routinely using examples to just quickly synthesize the bits that this is going to be good at, and we're working on the rest? Or do you see in 2030 as something much more revolutionary, where actually all kinds of shit is being built automatically and, magically?
So I think it will be a little bit in between, because one thing that I haven't talked about, and there's people here in the audience that know much more about that, is actual program synthesis, right? So these machine learning things are you create a black box. But I do think there's if you look at the advances in program synthesis, so there will be pieces of code that are generated by some machine, and then there will be other pieces that are proven correct. But ultimately, you will, I don't think there will be everything will be learned, or everything will be proved correct, or everything will be synthesized. So some human will have to compose these things, and I think, again, monads and effects will play a very important role, because all these different systems that you compose together will have different constraints, right? It will either return a probability distribution, or it will be slow, so you have to compose those. Now the other thing, I think in terms of software engineering problems there, it's think of this: how do you debug these systems? How do you maintain them? That's a nightmare too, which is also good for our job security.
Your example with the P made me think of our love-hate relationship with abstraction. We love it because it allows us to do stuff like that, and we hate it because it hides away details that later we come to care about. And you even just used the word black box for these machine learning models. And it seems like in the area of adversarial machine learning, for example, the fact that it's a black box is a big problem. So I'm wondering, have we just shifted the P here to be a different, uglier, funnier looking P, and what are your thoughts about that?
Yep, absolutely. Let me get up here. Absolutely. You see this guy, little guy there crying on the floor? Yes. So again, yes, I think that's maybe the bane of our existence, right? Yes, we're just shifting the P, because right now it's kind of scary, and that's also another reason why I don't believe that these neural networks are intelligent, because you change one bit and instead of a dog it thinks it's a bowl of guacamole, right? So I mean, if this thing really understood what it was doing, you couldn't just change a little bit of the input and get so much different in the output. So yeah, so there's a lot of uncertainty here, and that's also why my last slide is I hope that this thing doesn't bite itself to death, because maybe because of those problems, the whole thing will collapse. But I have good hopes. Again, if we as programming language people jump on this, how do we debug these things? How do we understand these things? This is all program, because ultimately a neural net is just a composition of functions, right? So we should be able to reason about it and say more about it. So again, I'm super serious. We as a community should jump on this and use all the knowledge that we built in these decades of PLDI and POPOS and apply this to this field.
I have a question that's a little bit of a follow-on to the first one. the observation is that automatic differentiation applies also to imperative programs. So could you comment on the ability of having a mixed system that has a sort of classical component and a learned component, but where there is also a backpropagation through the classical component, and the potential of that as a way forward?
Good question, very good question, because like, again, like, let me get, like, you know, give my like toy program here. So like maybe what you're asking is, can I take a system like this where there's like classical components and other components and like backpropagate through there? I have heard people say that they can do it, but I haven't seen it. And the reason that I can, like, you know, I think, but so my assumption is that you cannot do it, right? Because that's like, you know, making a web service call, like, you know, that goes through your kind of network stack, whatever, I cannot imagine that that will ever be differentiable. I mean, the inputs are not even kind of like continuous things, right? So,
but these systems have existed for 20 years.
So then we should talk. Then I would love to hear about that, but because maybe then this is not necessary.
I mean, they have their own problems as well, but they do exist.
Okay, let's talk. All right.
All right, thank you. Excellent talk, thanks. So I'm curious about your thoughts on what would make people comfortable with these kind of compositions of techniques in terms of, we have uncertainty at one level, at second level, third level, all levels. How to make them comfortable on one hand, and on the other hand, what it means for developers, how do they tune these systems?
Very good question. And again, I think, like, you know, these probability distributions are really weird effects, because the things like, you know, like as many like, you know, things like people don't understand, say, Bayes rule, right? If you ask doctors like to explain something, they kind of get it wrong, because a lot of this statistics is very counterintuitive. And now you're writing complicated programs that are composing probabilities. And that's, again, like I point to that slide where this guy, like the little person there is crying. I think this requires a lot more advanced debugging techniques, testing techniques that we haven't even solved yet. And again, it might be, that's why I have the snake in the end, it might be that it's just too hard to solve, and the snake will kind of like kill itself. But right now, for example, what we're trying to do inside Facebook is we're trying to get like be able to get like, you know, you can hover over these sample points, and it will show you the distribution that is computed there. So you can kind of like understand, like, you know, what happens along the way. But it's like, you know, there's a lot of software engineering problems here to be solved to get like make this usable for normal people.
Thank you.
Thank you.